Good afternoon, class. In today's video, what I'd like to do is to start a new series of videos about electricity. And in this video, what I'm going to do is I'm going to start by giving a general overview of all of the concepts that electricity brings, both in the sense of how it is similar to what we have studied before and also how it is different. So to do that, in order to begin that, I need to introduce a new fundamental unit for you to think about, and that is called charge. We did talk about this in the beginning of the school year when we talked about base units. So this is the final base unit that is being introduced this year. So we start with the unit of charge, and it is a fundamental unit that all atoms and all matter has. How it relates to the other fundamental units is very different, but all atoms have it in the same way that every bit of matter in the universe has mass, length, time, temperature. It also has a charge. How well that charge interacts with other matter is a subject for debate and for further scientific investigation. So the name of this charge is called the Coulomb, and in variable form it is given by the letter Q, lowercase q. When it is uppercase q, that is also used, but not as often as lowercase q. So for now, I'm going to be using just lowercase q for when I write all of these equations. If I need to use the uppercase q, I will do so, and I'll let you know when I do that. So let's start with some similarities, because we've already covered quite a few equations in physics so far. So what you should start to see is that there is actually a pattern that emerges when it comes to electricity, as well as what we did in mechanics in the previous semester. So let's take a look at that. We start off with some of the forces that we remembered. F equals g m1 m2 over r squared. This is the force of universal gravitation. Then we have F equals ma. Velocity is equal to distance over time. And of course, potential energy is a force times distance, which is gm1 m2 over not r squared, r. So in the same way, this is where electricity is very similar to mechanics, or the mechanical physics that we've studied so far, in that we have Coulomb's law, which is force is equal to k q1 q2 over r squared. Force can also be written as q, or the charge, times the electric field. I, which is current, which is charge over time. So so it's a measure of how much charge flows through something over a period of time. And then we've got voltage, which is electric field times distance, which is also kq over r. This is also known as electric potential. Okay. Now, those are many of the similarities that come from electricity in terms of electrical equations. There are actually more equations than this. This is just where these similarities are between what you've studied before and what you're studying now. Now let's go to some of the differences, because first off, I didn't define what any of these terms are, and I'll be doing that in subsequent videos where I actually go into them a little bit in more detail. This is, again, a general overview of electricity. So the differences where there are no real where there's no analog in terms of mechanics formulas, are the electric field, which is kq over r squared, and then there is also this resistance that comes from when electricity tries to flow through a wire. This would be, the resistance is how much it holds the electricity back and it stops it. Kind of like friction. I don't want to go into too many analogies here because this is a general overview. When I go through each of these equations in a little bit more detail, then I'll use those analogies, and we'll talk about how to parse the difference between all of these different concepts, because I don't want to get anybody confused. What you understood from here, in terms of mechanics, does work when you talk about electricity. There is a difference, though, and the difference is that whereas in mechanics, there were some limitations in terms of which way the force traveled. You know, force can be in general point this way, this way, this way, or this way, and up or down as well. And they all have their places. But especially when we're dealing with gravity, we always knew that gravity was only attractive, that it only pulled in what I defined in other videos as the downward direction. However, with electricity, electric forces can repel and attract. So if you try to understand it the way that you understood gravity, you're going to find yourself getting confused, because there are some specialties, some special ways of working through these equations, even the concepts themselves, that we don't deal with in our everyday lives, so they become not as intuitive. For example, most of you have already seen what happens if I take a marker like this and I drop it. You can see that very well. However, nobody has seen an electron flow through a wire. We know electrons flow through wires, we've just never seen it before. In fact, even this video is being utilized through electrons moving through wires, electricity flowing. What does that look like? I can give you analogies, I can try to do all of that stuff, but it doesn't quite show the reality of what's going on, and that's why a lot of times electricity, just to be clear, can be seen as somewhat a more difficult conceptual subject than mechanics, because we don't have as much real-world experience as we do with mechanics. So that's something I want you to consider. I'll go into more detail in future videos. I just wanted to make sure that you had a general overview of some of the equations that come about through mechanics and how they are similar in electricity, but also can be very different. And we will discuss those concepts next time. Good luck in your studies. May the force be with you.